Hi everyone, I'm Johnnatan Messias, a PhD student at the Max Planck Institute for Software Systems and at the Universität des Saarlandes here in Germany. Today, I'm going to talk about our work, selfish and opaque transaction ordering in the Bitcoin blockchain. First, let me explain what is a blockchain. A blockchain is a decentralized P2P ledger and append only list of cryptographically linked records of transactions called blocks. Participants called miners are responsible for choosing and including the issued transactions in a new block and extending the blockchain by solving a cryptographic puzzle. As we can see, blockchains have a lot of interesting properties like decentralization, immutability, transparency, and they are also tamper evident. Because of these properties, there have been several applications built on top of blockchains. For instance, this includes decentralized finance or DeFi applications like payment and money transfers, decentralized exchange, and many others. One of the key things that matter given all these applications is the transaction ordering prioritization. For example, how quickly are these transactions getting executed or included by a miner, and in what order are these transactions getting executed? Then, in this paper, we focus on transaction ordering. Let's first understand the part of the blockchain that is relevant to transaction ordering. The first thing is, everyone can issue a transaction through a peer-to-peer network. These transactions eventually will reach all the nodes in the network. Each node has also a store of these transactions called mempool. This is simply a pool of all transactions that arrive and are pending for inclusion into a block. Periodically, the mining pool pulls out some of these transactions from the main pool to include in a block. The transaction order depends on what transactions the mining pool select, then from the main pool. After they selected these transactions, they put them in an order within the block. Finally, as soon as the mining pool mines the block, they relay it to the peer-to-peer network, and the block and all its transactions become part of the blockchain. Now, let me tell you 3 assumptions everybody makes today about transaction ordering in Bitcoin. And these are the norms that everybody thinks are being followed. For instance, which transactions are allowed or even transmitted over the peer-to-peer network? If a transaction offers a fee below a certain threshold, it will be dropped and no longer considered for inclusion. By the way, the fee here is simply the money that miners get to include this transaction in a block. Therefore, here we have the first norm, fee rate threshold for excluding transactions. Now, once these transactions get into the main pool, how are miners selecting them? This is the second norm, fee rate-based selection when mining new blocks. And then, once miners select these transactions, in what order do they get included within a block? This is the third and final norm, fee rate-based ordering within blocks. Essentially, these are the 3 norms everyone expects that are being followed. Now, let me show you whether or not these norms are being actually followed. Therefore, we analyze the norm adherences next. Regarding the first norm, our findings suggest that while all miners largely follow the norm of ignoring transactions, offering less than the recommended or suggested fee rate or 1 Satoshi per byte, a few occasionally deviates from this norm. For example, our Bitcoin node received in total 1,084 low fee rate transactions. Now, about the second norm, we checked if the transaction fee rate is the primary or the sole determining factor in transaction ordering. Then, we sampled 30 snapshots of our main pool to check for transaction pairs, where if one transaction was issued earlier and has a higher fee rate than the other, but was committed later than the other, then we have a clear sign of violation. We found that a non-trivial fraction of transaction pairs violates this norm across all snapshots, clearly indicating that miners do not adhere to the norm. Now, finally, following the norm 3, we can predict the precise position of each transaction within a block. Then we propose a metric called position prediction error, or PPE, to measure how far away these transactions' positions are from this norm. We found that the mean PPE is 2.65%, indicating deviations within block. Also, 20% of all blocks have PPE higher than 4%. As we can see, most of these norms are being followed by miners, but a fraction of transactions violates these norms assumptions. Let's now investigate these norm violations. To understand why there are some violations, we came up with three hypotheses. What if the miners have some vested interest in the transactions they are including? If the transaction is of interest to the miner, then maybe they are unfairly prioritizing them. For example, when the miner is a sender or a receiver of Bitcoins, they may have an incentive to selfishly accelerate the commitment of such transactions in the blocks mined by themselves. Now, what if the miner was dropping some transactions because it was from some scam payment? If the transaction is part of an scam payment or ransomware, then maybe the miner doesn't want to include it. We look at some data on the web, and then we identified some payments as a scam and look at if some miners avoided including them. Bitcoins are increasingly being used to launch a variety of ransomware and scam attacks. Then our hypothesis is that some miners might decelerate or even absolutely exclude the commitment of scam payment transactions out of fear or ethical concerns. Finally, are miners allowing users to pay a fee for prioritization via side payment channels? Maybe the miner is getting paid something off-chain through side payment channels to prioritize these transactions more. Recently, some mining pool operators have started offering transaction acceleration services, where anyone wanting to prioritize their transactions can pay an additional fee to a specific mining pool operator via these side chains. Such transactions fees are dark or opaque to other mining pool operators and to the public. And then we hypothesize that some of the committed low fee rate transactions might have been accelerated by using such services. We investigated all these three hypotheses. For details, please refer to our paper. But let me now explain how we investigated norm violations for self-interest transactions. To investigate self-interest transactions, our trick to infer these transactions was the following. First, we identified wallets that belong to the mining pool, as the transactions involved those wallets should be of interest to the mining pool. Then we looked for transactions that use these wallet addresses. To detect whether a mining pool has accelerated or decelerated the above types of transactions, we first designed a robust statistical test that enabled us to identify that all these miners were indulging in selfish interest transactions prioritization. Our statistical test relies on the following observation. Suppose everybody follows the same norm and prioritizes the transactions in the same way. Considering then a set of 1,000 transactions where 100 of them are from mining pool operators, if all miners mining following the same norm, then the fraction of these transactions that each of the miners should mine should be hopefully proportional to their hash capacity. But if the numbers are very different, much below or much above, then there is a differential prioritization. For instance, here we see that Alice deprioritized some transactions and John prioritized some transactions. The beauty of this test is that now we can look back at the history of the blockchain and check what fractions of transactions included by different miners were prioritized or deprioritized by them. This is the test we used. Let me now tell you the results we got. Our analysis shows the following. We used this statistical test for self-interest transactions and found that mining pools prioritize their own transactions, but worse, they also prioritize other mining pools transactions. We also used this statistical test for scam payment transactions, but we didn't notice that any mining pools prioritized or deprioritized transactions. This could be a good thing, but it also raises a concern about whether it is good or not. Regarding dark fee transactions, using a signed version of the PPE measure I mentioned before, we confirm that a significant fraction of transactions has been accelerated via side channel payments. These transactions were wrongly positioned within a block. Please check the details in our paper. Finally, let me summarize our results. We found that transaction ordering is critical for blockchain applications. Today, the conventional wisdom assumes that every bar follows the three norms, but all three norms are violated today for a variety of reasons, including selfish prioritization and non-transparent, opaque, dark fee payments. Finally, our work opened up many interesting questions for future investigations and designs of blockchains. For example, what are the right prioritization norms? Should miners be allowed to differentiate transactions based on their data or content? How can blockchains enforce the right prioritizations by miners? By the way, our source code and our scripts are publicly available on GitHub repository. Thank you so much.